Hello, this is On from Habib University, and this is my electrical machines case study presentation. The topic for today is brushless DC and AC induction motors in electric vehicles. These are some of the abbreviations which I would be using throughout my presentation: electric motor, electric vehicle, alternating current, induction motor, synchronous motor, brushless direct current, electric drive, switched reluctance motor, permanent magnet synchronous motor. I would start by discussing a brief history of electric vehicles, then I would go on to describe some of the electric motors used in electric vehicles nowadays. I would discuss the contributions of my case study in this presentation. I would then discuss the design and working principle of AC induction motors and brushless DC motors and compare both of these motors. I would then perform an analysis on their power efficiency, torque, speed characteristics, and design cost, and propose applications in electric drive specific to the performance of those motors. I would then conclude the findings of this case study and establish the performance of both the brushless DC and AC induction motors in different scenarios for electric drives. The first electric motor was invented by Thomas Davenport in 1834. This opened new pathways for electrical engineers and designers, but the first electric vehicles were not built until the early 1900s. Although the genius invention of Nikola Tesla in 1887 about the AC induction motor opened new doors for electric vehicles design, the electric vehicles didn't gain a lot of popularity until the 21st century. This is because of a severe blow struck by the gasoline-powered engines and Henry Ford's mass-produced Model T, which was introduced in the early 1900s. Because of their extremely powerful engines and wide availability of gasoline and fuel throughout the world, the gasoline-powered engines took the electric vehicles market. In 2000, the first hybrid electric vehicle was introduced by Toyota, called the Toyota Prius, which gained popularity, and since then many industries have been spending and investing in electric vehicle designs. Electric vehicles have gained popularity and are one of the most used vehicles nowadays. These are some of the motors that can be used in electric drives and electric vehicles. DC motors, induction motors, synchronous motors, switched reluctance motors, brushless DC motors, and permanent magnet synchronous motors. All of these motors have their own advantages and disadvantages, but and are very specific to electric drive case scenarios. But in this case study, we would be discussing just two of these motors and comparing these motors in different electric drive scenarios. That is the brushless DC motors and the AC induction motors. The contributions of this case study is performing the comparison of the construction and working principle of brushless DC and induction motors, analysis of the cost effectiveness, power efficiency, torque, speed characteristics of brushless DC and induction motors, electric drive applications of brushless DC and induction motors based on the trade-offs established in the design and working principle. A brushless DC motor consists of a rotating permanent magnet, which is also called the rotor. It has a stationary stator which has 3 or more phase wound on it, a position sensor for rotor, and a solid-state electronic switching circuit to control the phases of the stator based on the rotor position sensor. It works on the working principle: a permanent magnet current carrying wire in the presence of a magnetic field has a force induced on it. As you can see, the permanent magnet rotor or the field is rotating with respect to the phase windings of the stator coil, as the stator coil's windings is controlled by an electronic controller which receives a feedback from the sensor about the current position of the rotor and switches the stator phase magnetic poles based on that, which causes the rotor to rotate due to the torque induced in the rotor, which is given by the following formula on the presentation slide. An AC induction motor consists of a squirrel caged rotor which is rotating, and which is also the field, and the stator which has 3-phase AC winding, which is also stationary and is also called the armature of this motor. It consists of a PWM inverter to control the voltage and frequency of the stator coils, hence controlling the rotor's speed. It works on the working principle. A time-changing magnetic field induces a voltage in a coil of wire if it passes through that coil. As you can see, when an AC power supply is provided to the stator coils of an AC induction motor, it generates a rotating magnetic field which rotates at the synchronous speed given by the formula on the slide. This rotating magnetic field cuts the stator coil bars and induces an EMF which produces a current which then produces a torque on the rotor, and the rotor starts to rotate. Note that when the rotor starts to rotate, it produces its own magnetic field which is called the rotor's magnetic field. The rotor's magnetic field chases the stator's magnetic field and ultimately rotates at the same speed. Note that the rotor does not rotate at the same speed as of the rotating magnetic field. This is because if the rotor starts rotating at the same speed, there would be no magnetic field lines cutting the rotor cage bars, and there would be no EMF induced in the rotor bars, and hence the rotor would stop. As a result, the rotor rotates at a slower speed as compared to the rotating magnetic field, and this difference in speed is given by the formula for speed slip, which is the difference between the synchronous speed and the rotor's speed. To understand the performance of each of the motors in different electric drives scenarios, we have to understand a typical electric vehicle and its requirement. A typical electric vehicle requires a longer constant power range. It requires high torque, less torque at high torque at smaller speeds. For acceleration and climbing purposes, for credibility purposes, it requires high power at high speeds, and it requires fast torque and robust and efficient. Now we will analyze whether our motors can contribute to a typical electric vehicle requirement. A brushless DC motor, because of its design, is very cheap. It's not cheap at all, I'm sorry, it's very expensive because of the rare earth metals used in the brushless DC motor. It has more complicated controls, although it is more power efficient because of the permanent magnets and less windings used as compared to an induction motor, where it's more expensive as compared to an induction motor. Brushless DC motor functions best at smaller speeds and smaller speed and high torque, and cannot provide constant power for a longer period of time. Hence, they are used where electric vehicles are drove at where electric vehicles drive at slower speed and where high torque is required for acceleration purposes. An AC induction motor has a simple design and are cheaper. They have more power losses because of the stator and rotor windings, but an induction motor provides a high starting torque. They provide a longer constant power region. They also provide at high speed. They are good at high speed and low torque regions, and hence perform better when the electric vehicle is driving at a faster speed and it's less frequently stopping and less frequently accelerating. A study based on the finite element analysis was carried out for both the brushless DC and induction motors, and it was found that the brushless DC motors perform better in the city scenarios where there were more frequent starts and stops, the more frequent high torque was required, and the more frequent acceleration was required, where the speed was slower as compared to a highway where the AC induction motors perform better, where high speed and high constant power was required and there were less frequent start and stops. This study proved that AC induction motors are better at high speed, low torque scenarios, and brushless DC motors are better at low speed, high torque scenarios. Tesla Model S, Tesla Model X are some of the examples of AC induction motors, and Toyota Prius as an example of brushless DC motor, as discussed before, whereas the Tesla Model S is the example of AC induction motor. The conclusion is obvious. A brushless DC motor are well suited for applications of low speed and high torque. AC induction motor perform better in applications where high speed and low torque are required. Induction motors are cheaper and offer good speed controls. Brushless DC motors are expensive and use complex electronics for speed control. I hope you had a great time listening to my presentation. Have a very nice day.